My name is George Schmidt. I'm the chairman of the Asteroid Foundation, and I have the great pleasure in welcoming you today at this very first event of our Asteroid Day celebration, actually our 5th anniversary Asteroid Day celebration here in Luxembourg. So this technical briefing is all about science, what's going on in science and excitement from people who have been up there. But before we start, in order to set up such events, we need lots of help. Help from all of you, speakers, but also help from our sponsors. And so I'd like to recognize our sponsors to start with. First of all, of course, Arendt, who provide this superb venue, air-conditioned, when outside it's 33 degrees. What else can you ask for? Thank you very much to Arendt law firm for this second or third opportunity, I think. That was going to be my last word. So, but also a lot of other sponsors. The Luxembourg Space Agency has been with us for the past 3 years. SES, Broadcasting Center Europe, B612, of course, OHB, Eurocomposite, Sofitel, Chamber of Commerce of Luxembourg, New Space Capital, Tomorrow Street, the Luxembourg Association of Aviation and Aeronautics, and finally, Lush, who is our transportation provider. So with that, I hope you will enjoy a fantastic afternoon, and I would propose that we work for air conditioning and turn it down a little bit. Don't catch a cold. Danica, I'd like to introduce Danica, our Secretary-Treasurer of the Luxembourg Foundation, so she has all the money.
Thank you, George.
Yeah.
So I'm really excited to be here today. We're going to start off with a short movie to kind of give you all a sense of what we do for Asteroid Day around the world. So if I could have the lights go down.
Ed Lu has been to space 4 times, and during one mission lived on the International Space Station for 5 months. With a bird's eye view of the moon and the many craters caused by asteroids, he reminds us that our Earth is impacted more than the moon. Asteroid Day Live is the only programming dedicated to introducing you to many of the most prominent asteroid experts in the world. We learn by listening to them share their personal experiences and knowledge of how our solar system was formed, how it is evolving, and how we can protect our beautiful blue planet. But this programming wouldn't be possible without the generous support of major sponsors, including the Government of Luxembourg and you. You play a critical role in our ability to shine a bright spotlight on the leading work of astronomers, engineers, scientists, space mission operators, and astronauts, our global rock stars, who bring the topic of asteroids closer to people of all ages and remind our government leaders of the importance of funding planetary science. Asteroids play an important role in our lives, from the formation of our solar system to their extraordinary value for future resource utilization, to enabling ongoing exploration of our solar system, and finally, when they impact our home planet. Asteroid Day is more than just a broadcast program. It's thousands of independently organized events in 192 countries. These events are the heart and soul of Asteroid Day, as they connect and engage students on the subject of asteroids. For many students across the world, Asteroid Day is their only opportunity to listen to, learn from, and to meet astronomers, astrophysicists, and astronauts, heroes of the STEM generation. Your support enables the growth of our network of independent event organizers, so more events can take place. It allows us to not only encourage the future generation of scientists, but to grow our online library of educational tools, enabling more people to dig deeper into asteroids and to connect to scientists, observers, and astronauts, Your support enables us to meet the goals of the United Nations Office for the Peaceful Uses of Outer Space Affairs by generating awareness of what we can do to protect our planet. Please consider becoming part of this movement by donating to Asteroid Day today.
So you can bring the lights back up. So you just have seen the debut of one of 5 trailers that will be premiering on Asteroid Day Live tomorrow. This one starred Ed, and we have one starring Rusty. We have one starring Doran as well, who've been integral to the growth of the interest in asteroid awareness. And Rusty has been a co-founder of Asteroid Day, and that's why we're all here celebrating. My colleague Greg Richters is in a hot truck over at BCE Studios, putting together slices of films and the straps that will show up in front of many of the speakers who are here in the room tonight or this afternoon on TV worldwide. And we have a partner this year called Twitch TV that allows the programming actually to make it into China. So we're excited about the global audience that will be made available online. And of course, it's being broadcast worldwide through SES's satellites to over 100 million homes in the world through their 4K demo channel. So we're really excited to be bringing all of this to the world from Luxembourg. And we host this particular event to say thank you to our partners and to the community here in Luxembourg for being so generous in your support and bringing us, Asteroid Day, this global program, to Luxembourg. So as George said, our home is here in Luxembourg at the Asteroid Foundation, a Luxembourg-based charity. And the Luxembourg industry has really made so much of what we've been able to share with the world public through the relationship with SES and BCE. As well, this year we've rolled out a new program called Astronauts and Experts, where we've been bringing both virtually and in person astronauts and asteroid experts to students around the world. This year here in Luxembourg, let's see, Michelle Togini is going to go to a school tomorrow. Reinhold was at a school this morning. Doran is going to a school on Monday. And I can't remember who else has done a virtual one. But we've just started to roll this out. So we've done 6 here in Luxembourg, and we'll do a few more before the end of the year. And we've also been sharing astronauts with our independently organized events in other countries around the world, because we have an incredibly strong partnership with the Association of Space Explorers. So every one of the gentlemen sitting up here in the front of the row are members of the ASE. And part of the reason why Asteroid Day was able to accelerate at such a rapid rate at such a global level was in part having a founding partner like Brian May doesn't hurt, who also happens to be an astrophysicist. But the Association of Space Explorers under Rusty's leadership many years ago, 15, 18 years ago, I don't know the number, started, how many? Our friendship is 36 years, that's true. But the ASE started the Committee for the Near Earth Objects in 2005, and it was because of the ASE's early work at the United Nations that when we launched Asteroid Day, within, I think, 16 months, Doran had presented to the General Assembly at the United Nations that the United Nations should consider endorsing Asteroid Day as a day of education and awareness worldwide. And so I'd say that part of what has really made it possible for Asteroid Day to accelerate has been the early leadership from the space travelers and part of the Association of Space Explorers. So we're incredibly grateful for them to come to Luxembourg, to have been speaking on behalf of asteroid awareness, asteroid science, asteroid planetary science. They've been really, really helpful in helping us build this global movement. And so we're here today to say thank you to all of you and share some of the expertise of the scientists who are working in this field today. And so I will introduce you one by one as you come on, but Mark Boslough is the chair of our Asteroid Day expert panel. He's going to start. And then Robert Jedicke from the University of Hawaii will come next. And then Slava from JPL will come third. And then Lynn Jones from the University of Washington will come fourth. And then Patrick Michel, who's working actively on 2 asteroid missions, will go last. The format will be after they present. Our space travelers will ask the speakers questions. And then I'll moderate. And then we'll open it up, if we have time, because we're trying to keep to a time schedule, we'll open it up to the audience to ask questions. So it will be a presentation, questions from the space travelers, questions from you. We're going to repeat that 5 times, and hopefully we will be out of here in time for the reception at 4:15. So with that, I would like to ask Dr. Mark Boslough from now Sandia Labs, correct?
Now Los Alamos.
Los Alamos,
Yes.
to come up and talk to us about
Are small asteroids more dangerous than we think?
That's right. Thank you. Small asteroid. And I'm going to keep time. I'm going to keep time because scientists like to talk for a long time, so I'm going to cut them off.
Have we underestimated the asteroid, the airburst risk? And this is more than just a rhetorical question. It's a question that I think we have the capability to answer. This is an artist's rendering of an airburst, a small asteroid like Tunguska exploding over Los Angeles. And artists and movie makers like to destroy cities. Here's London being destroyed, and we scientists have told the artists and documentary makers that yes, airbursts can destroy cities, but what we can do with our sophisticated hydrocodes is actually quantify that. I had the opportunity to do this for our most recent Planetary Defense Conference, which was just a couple months ago. And so we like to do these tabletop exercises where we have a scenario where there's an asteroid on a collision course. In this particular scenario, there was a collision course with Denver, with downtown Denver, and it was at the time of this simulation was a 200-meter asteroid. So I'm just going to show you a simulation that I did for a 200-meter asteroid colliding with Denver, and I took that skyline and I found a silhouette of that, and I found the scale, and then I put an asteroid that was a similar scale. I used a contact binary. That was our scenario, but it had the mass of something that would be 200 meters in diameter. I also put Tunguska on there just for scale. And so this is kind of the scale of the central part of Denver and suburbs. And so I entered this asteroid, and this is what it looks like. This is actually the Tunguska-sized asteroid. So that would be downtown Denver being completely wiped out. Now, I don't have a temperature scale on here, but the highest temperatures there are about the temperature, set thousands of degrees, roughly the temperature of the sun. So anything at ground zero would be completely vaporized, and the sort of cyan bluish color is the shock wave, a blast wave, very similar to the one that knocked down the trees at Tunguska. In the scenario, we had a partial deflection. We actually deflected the big part, but the little part that was the contact binary was not deflected completely off the Earth. And wouldn't you know it, it went straight to New York. So here's the same thing I did for New York. This is a 60-meter asteroid. And again, there's the skyline, and it's a smaller impact. It comes in at a steeper angle because it's a different position along that risk corridor. So we know, in fact, that an asteroid airburst from these simulations actually does more damage on the ground than a nuclear explosion of the same yield, and that is because all this energy continues to move downward. So I'm not going to go, I know Danica will kill me if I go through this in detail, but this is our chart where we kind of make this tacit assumption when we do this risk assessment that risk is uniform, that everything is kind of uniformly distributed, and there aren't any dense clusters of asteroids that the Earth could encounter. But that's not necessarily true. We don't have any observational evidence that there aren't. We don't have strong observational evidence that there are, but we have some hints that there are. The reason this is interesting right now is because there is a group of researchers that have done work on what they call the Taurid complex. And it's kind of like a meteor stream, except it could have dangerous asteroids embedded within it. That's the argument. So the yellow is the orbit of Jupiter, and the blue is the orbit of Earth. I think I actually have maybe not. That's too weak. So the red is the orbit of this Taurid complex, which is the remains of Comet Encke. And there could be a dense cluster that is actually focused in this resonance, according to some orbital dynamicists. And there's actually a table on the left. There's two encounters, one in November, that's the nighttime Taurids that come in, and then it goes around to perihelion and it comes back up, and there's another encounter in late June, which is right now. And there's a reason for that. This is Asteroid Day. So in 1975, there were a lot of active seismometers still on the moon. This is one being placed by Rusty's colleague Buzz Aldrin, Apollo 11. And there was a lot of seismic activity in late June in 1975 that a lot of people are associating with that, associating with the Taurid complex. And if you look at the table, 1975, the mean anomaly is actually very small. That's a measure of the distance of the miss of if this complex, this dense cluster, if it exists, that's how many degrees it would pass the Earth when it crosses the Earth's orbit.
Delta M means in this.
I'm sorry?
Can you explain what delta M means?
Well, it's the mean, basically it's the mean anomaly. So it's I mean, one way to think of it in simple terms is like a clock. So you know, if the Earth is moving around its orbit like a clock hand, and the Taurid swarm is also moving around in this elliptical orbit like a clock hand, and that's like the number of degrees between the two hands of the clock at the time they cross the same orbit. Is that?
So you're making it so 0 is with the Earth?
Right, yeah. So in 2015, the November passage of this swarm created a lot of bolides that were actually documented. So there was an increase in the number of large bolides, meteors that explode in the sky. And so there's some evidence for this. And here you can see the tables again. Now we think that Tunguska might have been a beta Taurid. It's completely consistent. So these are my quantitative simulations of the effects on the ground. The middle map is actually a map of tree fall, and it's rotated by the direction, my simulations are rotated by the direction that's consistent with the direction a beta Taurid would have come from at that time and at that place on June 30th, 1908 in Siberia. This is a series of simulations that show different elevation angles. If it came from almost vertical to a very shallow angle, the map again rotated to be consistent is in the upper left. That's observed, and it's most consistent in my, discrete set of entry angles with 35 degrees. A beta Taurid would have been 32 degrees. So again, it's quite consistent. This is a poster we presented. I can make this available. But I want to point you to the lower right corner. We propose an observational campaign this summer because that delta mean anomaly is only 5 degrees right now. So it's passing right now. And this is, Peter Brown came up with this idea last summer, and one of his colleagues at University of Western Ontario created some simulations. This is the beginning frame of some animations that are available on his website. This is right now. This is June 27th. So this cluster is very, very spread out. And so some of these objects should be observable from Earth right now, if they exist. And they will be observable if they exist for the next couple of months. Here's the view from the Earth. And so this basically is a guide to observational astronomers to guide them where to look if they're doing surveys looking for particular objects in this cluster. And you can see one of the things I want to finish up with is if they are discovered now, the next close passages are in 2032 and I can't see it from here, I can't see my numbers, but I think it's 2032 and 2035. So I want to finish up with this. There's also some very interesting phenomena going on in the sky right now called noctilucent lights. They're noctilucent clouds. They're very rare. They've never been observed as far south as they are this summer. That may be a clue. It may not. It's like an idiot light in your car. It may go on and you may not know what it means at all. So I'd be happy to answer any questions.
Mark, I'm wondering what I'm wondering what you see out of this work in terms of its implications for planetary defense. Are you suggesting that clustering may be very common, or are you seeing this still as an exception? How do you see this affecting the way in which we think of planetary defense?
Well, I think, so David Asher was the dynamicist that did the original work with Napier and Klube and those guys. And I was quite skeptical, but there could possibly be this dense cluster of significant objects, and that the Earth passes very close to quite often. But it's always been too far away to observe since we started planetary defense-related surveys. So we haven't counted those in our probability estimates. Now, if we come very close and get bombarded occasionally, that might explain why, for example, Tunguska, which should happen, assuming the sort of homogeneity and uniform probability, it should only happen once every 1,000 years or so. It happened a little over 100 years ago. Maybe the probability changes with time. And when you pass close to one of these swarms, the probability for a short period of time goes up much higher than the background probability. And so we haven't accounted for that in our risk assessment. So if this observational campaign this summer shows that there really are a lot of objects in this swarm, that means we underestimated the overall probability integrated over time.
So you're seeing this as an incremental increase in the prior understood frequency of impacts.
Right.
So it's a superposed.
We've kind of always had this implicit assumption. I mean, we don't even talk about it, and it's just something we've always held, that probability doesn't really change with time. Everything's uniform enough that we can just kind of assume it's uniform, isotropic, time-independent probability. But if there is a tight swarm that comes close to the Earth occasionally, and the Earth may actually pass through it occasionally, then you get these periodic, very high probability periods of time, and if you integrate over time and include those, it could significantly increase the overall risk.
So I take it that the conclusion, if there is any kind of a positive result in the near term here, in this summer, for example, that the conclusion you're coming to is that you would recommend major changes in the focus of observing programs in order to see whether this is a common phenomena in all meteor swarm, whether this is not just something for this particular swarm, but for other major meteor showers.
Possibly, but I think the Taurids are the only example that have seriously been proposed as having this dense swarm, the Taurid complex. I'm not sure there are other examples of that. And right now is our observing opportunity. If you looked at that table, you don't have anything where it comes as close as this year until 2032. So this is our big observing opportunity for something that's not going to come close to us again for another 13 years. And then we're even closer. I think the delta M for 2032 was 1 degree, and now it's, I think, 5 degrees is this year. And it was 7 degrees last time when there appeared to be a significant enhancement. Ed?
How did they?
Oh.
in doing that calculation, how did you calculate or assume the width of the distribution, the width of the swarm? Where does that come from?
That comes from David Asher's work as interpreted by David Clark of the University of Western Ontario. So I'm not showing my work here, and so I don't know the details, but they actually just published their paper. It came out early last month, and so all the details are there, and I can send you a copy.
Yes, I have a question to the exercise you did. I mentioned it this morning. I find it very interesting and very valuable to prepare for these kind of things. Astronaut training prepares you also for the most impossible things, and once they happen, you at least have a hint how to progress. But that raises immediately a question of political ethics. I mean, how do you decide about deflecting this asteroid and having a smaller part hit another country, for example, than the US? Did you raise this problem? Was there an international representation? And would you rather leave nature to its course if you have to decide these ethics?
I think that's a question that there's been a lot of discussion about. I mean, I guess I would have to say that's kind of above my pay grade as far as making those kinds of decisions. I think I sort of feel like my job is to assess the risk, do consequence calculations, say that, you know, if you had something of this size coming and it was on a collision course, this is my best estimate of what would happen, and here's the range of uncertainty.
I should point out that those simulations are meant to be extremely unlikely cases, not to simulate the things that might happen, but to be extraordinarily unlikely, because that allows you to exercise all the decision-making processes. So you shouldn't consider the cases that are the exercise cases from the Planetary Defense Conferences as any way being a prediction of the kind of thing we're likely to see. In fact, it's exactly the opposite, because that allows everyone to play in the simulation.
True, but there's a...
Two things up here. You're talking about the Planetary Defense Conference simulation. Mark has been presenting a totally different thing. So.
Well,
Yeah, but he mentioned it, and
The decision making.
the decision making. How do you decide whether Denver is destroyed or New York? This is all in one state, but think of going transatlantic.
Absolutely, and in fact, you know, that is one of the reasons that we do these scenarios, and Paul Chodas is really brilliant at making them, you know, very pathological sometimes, like having a contact binary where you do your best to deflect it, but it's a contact. You've got one little piece sitting on a big piece, and you hit the big piece and it goes, and then a little piece gets a little bit of a delta V, and you don't know where it's going to go, and you actually can't know where it's going to go because when you do the deflection, it's not observable, and so you don't know where it's going to go until then it's too late to go to plan B. And so, you know, it kind of exercised that pathological possibility.
Reinhold, I want to emphasize what Ed said. You should never pay attention to what the Planetary Defense Conference desktop exercises are as being typical or characteristic of what might happen. They're specifically designed to be the worst case to force the thinking about what would you do if things were the worst case. It's a little bit like having 4 failures on your spacecraft at the same time. That's never going to happen, but the guys in the training outfit are going to do that to you just to see how you react. But it's not at all something we should be thinking about being realistic.
I think that's exactly the right analogy, Patrick.
And I have a question. Okay, I think the question was more either an international response, like political decision, and in fact, that's why the United Nations recommended 2 groups. One is called I1, it's International Asteroid Warning Network, which is composed of observers and the scientists who make the predictions. And if something happened, there is another group called SMPAGE, Space Mission Program Advisory Group, which is composed of space agencies who are responsible to give a response agreed by the space agencies. So that's where this was started thanks to the action of Rusty, by the way, at the United Nations. There was a team called Action Team 14, which recommended these two groups to be put in place. They were put in place only a few years ago. Whether they work or not, we don't know, because fortunately we don't have a real case. But it starts. And that's in order to avoid that somebody, then you will never prevent anybody to do what he wants, but in reality. But in general, we think that it allows to have an organizational response to this kind of problem. Just a quick question. We should look at the lunar flashes currently.
Yes.
Because we should also see a spike on the impact cratering on the moon and the lunar
good.
flashes.
Very good point. Yes, I agree.
Okay,
Thank you.
We didn't have time for the audience on that one. Okay, Dr. Lynn Jones, performance specialist at the Large Survey Synoptic Telescope that will be going live on a mountain in Chile in 4 years?
Well, it depends which
5
part.
years.
First light would be probably inside of 2.
Okay, first light in 2 years. And so, over to you.
So first of all, I have some video in here that has some audio, and I don't need the audio, so if you can mute the laptop, that would be great. Okay, so yes, I am Lynn Jones. I'm a research scientist working for on the Large Synoptic Survey Telescope, or LSST. LSST is a next generation survey project. You can see we're still under construction, but it's really nice. We have a almost complete telescope. LSST, when it's complete, it will join a big mirror. It's an 8-meter class telescope with a very big field of view, almost 10 square degrees. So you can fit 7 full moons across an LSST image, and the images consist of 3.2 gigapixels. So when LSST is complete, we will be able to survey the entire visible night sky twice inside of 4 days. And we will do that over and over during the 10-year survey lifetime. So while first light is coming up very soon, survey operations aren't supposed to start till 2022. So then we'll run till 2032. When LSST is in operation, we'll survey the sky over and over. This gives us a very deep stacked image that we can use to study very faint and distant galaxies. We'll also, however, because we keep looking at the sky over and over, we get sort of a movie sequence of images as well, and that lets us study variable stars, exploding stars, supernovae, but it also lets us study moving objects throughout the solar system, so comets, asteroids, even mini-moons, and interstellar objects like Oumuamua. LSST will be able to discover something as small as 140 meters all the way out into the main asteroid belt. And throughout the solar system, we expect to find about 10 to 100 times more objects of each population than are currently known, and that includes over 200,000 NEOs. So once we have the images in hand, the question of discovering asteroids in them is basically a question of software. And LSST is a survey project where we don't just have a telescope, we also have a significant software effort to make catalogs out of the images as well. So we will be going through to find moving objects. What you do in order to distinguish the moving dots that are asteroids from the stationary dots that are stars and galaxies is first we take the when we have an image, we create a template image from all the previous observations of that field, and then we subtract that template image from our new image, and that shows you the things that have changed. So this includes asteroids and variable stars, those supernovae, and then we go through and measure all the objects in that field. So in the center image here, you can see sort of a stack of 3 images. There's an asteroid moving between the top one and the second one, and this one's kind of easy to pick out because it's a trailed object. Most asteroids and moving objects in LSST images will not be trailed because the images are only 30 seconds long. But you can see that once you subtract the two, the object that was moving pops out. So at that point, you have all these measurements of things that are moving in different images, and it's playing a complicated game of connect the dots. So we use our various pieces of software to play that game of connect the dots and link up the different detections, and so that we can identify potential asteroids. We link the objects, determine an orbit, and send that to the Minor Planet Center, and that's publicly announcing the discovery of a new solar system object. Where it gets complicated is in this image on the bottom left there, you see simulation of the LSST field of view. So all of those little dots are asteroids throughout the solar system. So most of them you see are yellow, and those are main belt asteroids. There's a lot of them. So in a typical LSST image that is looking towards the plane of the solar system, you might have 5,000 objects. So, oh, this is where you can mute it if somebody has it. Or I can just talk if you can hear me. Okay, so discovering asteroids is important. However, we can do more than just discover asteroids with LSST. We can characterize them as well. That means determine their physical properties. So we did have a nice movie. This movie is made by Alex Parker from Southwest Research Institute, and it is showing, if it was continuing, that's okay, showing the moving objects, the asteroids discovered in the Sloan Digital Sky Survey, SDSS. So SDSS is an all-sky survey, or what was an all-sky survey, like LSST, but much fainter, and they only took a handful of images of each asteroid. So with SDSS, what you could do is you could discover the size of the asteroid approximately, and you determine that by looking at the distance to the object and the brightness of it. And so that's represented in the movie by the size of the dot. And then you can also determine the color of the object because they took observations in multiple band passes. So you can see, is it, does the object look red or does it look blue? With LSST, we'll also have so with LSST, we'll also have colors for the asteroids. We have a very similar filter set to SDSS, but we actually go further into the infrared. So we'll have a little bit more color information. So with LSST, we'll be able to determine these colors as well, and the colors tell you about what the type of the asteroid it is. So carbonaceous asteroids and metal-rich asteroids or silicate-rich asteroids all have different colors when you look at their representation in this bandpass. So learning about the color tells you about what the asteroid is made of. With LSST, we'll also have hundreds of observations for each object. So we'll not just be able to tell the color and the brightness, but we'll also be able to measure how the brightness of the object changes with the viewing geometry between Earth and the asteroid, and also as the asteroid spins. So we'll be able to see how fast it's spinning, and that tells you about what it's made of. Is it a rubble pile or is it a big solid rock? And we'll also be able to look at how its light changes with the orientation to the Earth, and that can tell you about the surface. Is it rocky or smooth? So we'll be able to learn more about the types of the objects, and for some objects, we'll even have enough observations so we can reconstruct a full shape model. So with LSST, we'll be able to learn a lot more about our solar system. We'll discover 10 to 100 times more objects across the solar system, including near-Earth objects. We'll be able to characterize those objects so that we can do things like discover what their physical properties are, but also we'll be able to look for potential spaceflight targets. We can find unusual asteroids, outliers in the population. We'll be able to find any potential planetary impactors. So LSST alone would find sort of about 60 to 70% of the near-Earth asteroids. And when you combine that with other ground-based surveys, it goes up to about 75 to 80%. And we'll just be able to study a lot and learn about the history and evolution of the solar system. And so now I can take some questions.
So over to our panel first and then to the audience.
Excuse me for for asking a question. I have two questions, actually. One is, first of all, we see a lot of satellites now being sent into space, thousands of Iridium-like and other satellites. How do you subtract them from your field of view? And the second question immediately, with this, do you use artificial intelligence to get rid of this background noise and see the real objects you want to see?
Yeah, so the Starlink satellites, yeah, for example, it's a good question. There's a lot of them, and there'll be more, yeah. And because LSST is at -30, we actually in the summertime we'll be able to see them for quite a while after sunset. And they're moving very fast. So you don't actually have a problem distinguishing them from the other things in the image. What you have a problem with is them wiping out large parts of your image. It's potentially I hope it's not as bad as MAGIC was for Pan-STARRS, but yeah, it's a good question. I think a lot depends on exactly how bright they end up being, especially when it's not towards sunset, and if they can do any mitigation for so they're not as bright as these first ones were when they went up. Some of the examples look pretty scary, but I think also we'll be able to hopefully do some mitigation with the survey scheduling.
Those were launched into a low orbit.
Yeah.
And as they raised up, they become very, very dim.
Yeah.
The SpaceX satellites were intentionally launched into a low orbit, which is raised. So the what you saw on night 1 is not at all typical. In fact, they're already pretty dim.
Yeah, it's a good question when our limiting magnitude for a single image is 24.5 rather than something brighter. But I think the LSST estimate is that it shouldn't be too bad. So as far as artificial intelligence, for these objects, because they're moving very fast, we don't need it for satellites. In terms of using artificial intelligence to discover asteroids and link up the detections, that's a good question. Honestly, I think a better place for doing some of that work might be, it really is not so much necessarily an artificial intelligence question, but it comes down to the statistics behind it, which is a lot of artificial intelligence work. And I think some of the really great places for that to be applied is in understanding what we're seeing when we get more measurements. So when we're trying to fit the light curve of the asteroids, for example, is this a good light curve or is it a bad light curve? It's really easy to fit something and you think it's good, but then you actually look at it yourself and you're like, oh, that was kind of crap. But that is some place where it seems like artificial intelligence and neural, CNNs and stuff like that would hopefully be useful. As far as finding objects, we've been working on algorithms to find moving objects and images for a long time, all the way back to Pan-STARRS and other projects, and that seems to be fairly well in hand. Although new approaches are always welcome. So.
Great. Questions from the audience? Got a microphone here.
Okay. For the images, the difference between two images as asteroids, this is dynamic. Is the dynamic difference? The difference between the image 1 and the 2 is dynamic object?
Yeah. So the example I had was a little bit of a bad example because it was just two images separated from each other. If you have a template image, that comes from many previous images, what you'll generally find is just the positive detection of the asteroid. So yeah, what you see in the difference image are the asteroids, any of the moving objects, but you also see anything that changes. So if you have a variable star, you will also have a variable star detection. If you have a supernova, you'll also have a supernova. If you have artifacts in the image, like glints from something in the optical path, you have that too. So that's where it gets a little bit more complicated. But yeah, especially towards the plane of the solar system. It'll be primarily solar system objects.
Another question, as you can have multiple images or from different angle with the new observation, can you give more like just from visual information you can estimate information like the depth of the object, or even like start building 3D representation of what you perceive as you have multiple images now? Is it something possible?
Oh, yeah. So when we have enough measurements for over enough different viewing geometries, you can start to build up that full shape model, 3D model of what the asteroid looks like. And there's been some really cool work with doing that with previous surveys. So I think that'll be one of the exciting things, is to see more full shapes of asteroids.
Other questions?
Are you going to render all the other surveys, Catalina and Atlas and so on, are they all going to be obsolete?
I think that they fill different needs, especially Atlas, for example, because one of the things that, because we do the entire visible sky every 4 days and not the entire visible sky every night, if there's something that's very small and coming in at the right angle or very fast, that might not be something that we would pick up, because we might just not be looking at that part of the sky. So surveys that can do the whole sky every night, even if they're doing it to a shallower depth, are useful in that regard. And then there will be, you know, Catalina doesn't have a super large field of view, so it can't do the entire sky every night, but there would definitely be like some follow-up opportunities, because a lot of the things that LSST will find are so small. They might require bigger telescopes to follow up, but there will also be a lot of bright things that are interesting to follow too. So, for, you know, maybe just for like getting a faster understanding of the orbit, or studying on different filters than we would have available, for example.
One more question?
I'm not sure if this is the right platform to ask this, but my understanding is that the camera, or the position of the camera, is at the tertiary focus in this, and it's not at the primary focus as in with most other telescopes. Is there a reason why this has happened?
So the optical design of LSST is sort of optimized, so it's very fast and it has this very wide field of view. And then also so that the telescope is compact. So I think to get, I actually don't know exactly the train of thought that led to the engineering choices that they made, but because the telescope has to slew and settle inside of 5 seconds, we can't have something that's very long, and most of the primary focus telescopes tend to be quite long. So it's a compact, short thing.
Thank you, Lynn. So next up, Slava Turyshev. This is flown all the way from the West Coast, along with Lynn Jones and Dr. Ed Liu. And you are from the Jet Propulsion Lab and NASA. So tell us about your satellites.
Excellent. We'll do that. So maybe first slide, I need to click here, right? So if I drive it here, what?
You have to click it.
I press on it. Which one to press?
Okay. Could we have some help in the booth? Is there still someone up in the booth? Just a moment.
All right.
Okay, he's working on it.
I see. Very good.
So do you want to...
I will be describing new technology. Essentially, something is coming online which is quite unique. And so this technology was developed basically in commercial sector. So the technology, the new sensors, CMOS sensors that we're using for processing the data, and also new computers came from gaming industry. And so essentially high processing power of those computers enable us to do observations and process them in almost in real time. We're talking about pentaflop computing that is available now, but we're using at this moment teraflop systems. So those teraflop systems that are already available commercially, you can put on a small telescope, and small telescope anywhere between 28 centimeters to 35 centimeters. And so putting this all together essentially makes a very major step in looking for faint, fast-moving objects. And so with this technology, essentially, we hope to change a lot of things in search for those objects. And so this is what I will be talking about. First of all, this is our home, right? So it's a beautiful home. It's nice to be on this planet. And so when I get the clicker, I will move to the next slide. I will show you the neighborhood, but now just enjoy the view of our home. And so at some point we'll get lovely. So this is our neighborhood. So let's look at the neighborhood, and we see the neighbors are quite many. So this is the middle part of the solar system. This is Jupiter's orbit. This is the main belt asteroids. So this is inner part of the solar system. So this is our planet. This is where we live. It's Earth, and you see quite a few red dots. So those little guys are the asteroids that actually cross orbit of our planet, and so they're potentially hazardous to us. So let's see what we have evidence. So we have potential, some neighbors are violent, and we see the evidence for this violence right here. So on the left, you see the chart from up to 200 kilometers in size. So quite a few impact craters on Earth. So also, these are some crime scenes that are very evident that asteroids hit our planet in different times. And you would think that this is all over. No, they keep coming. And so they keep coming. Essentially, what you see here, the two major events that happened only recently. So Chelyabinsk object that came in over Russia on February 15th, 2015. It was an object of roughly 17 meters in size, and it released energy of roughly up to 30 Hiroshima atomic bombs. So released in the atmosphere. So another object went above the Bering Strait in last December, and it was captured by satellites. As you see here, the shadow of that object just seen by a Japanese satellite, and that was a major event. That roughly 11 meters object. So, and energy release of roughly 10 atomic bombs. So we're talking about a major events happening as we speak, and this is for the last couple dozen years. So they keep coming. So what we can do, we need to study. The knowledge is the key. And so what we are looking for, we're trying to complete the search, looking for 140-meter asteroids. Why 140 meters? Because if an object with the size of 140 meters enters Earth's atmosphere, it releases energy equivalent to roughly 100 megatons. And so that's a major event happening in any region or even during the continent. So we don't want to have those visitors come in uninvited. And so we really need to know where they are. So this is the number of total discoveries of all objects. And as you see, the search began really in mid-90s, but it accelerated in 2000s. So by now, we know roughly 20,000 of asteroids. And so this is good, but we know that 140 meters objects are roughly just close to 9,000. And we don't know all of them. So potentially hazardous asteroids that actually cross orbit of our planet very close. So those objects are roughly 140 meters size, and we know roughly 2,000 of those objects. So this is not all that is out there. So we need to know more. So this is the completion statistics. Of the size of a kilometer size, those that we definitely want to see hitting the planet, we know pretty much every object. It's nearly complete. If you go down in size, the completion changes drastically. So in size of roughly from 100 to 300 meters, completion is roughly 34%. At the moment, given the statistics that you anticipate how many objects based on the known criteria, how many objects should be out there. If you go in the smaller sizes, objects anywhere between 30 to 100 meters. Remember, the Chelyabinsk event was only caused by 17 meters object, right? You don't want to have this object enter an atmosphere above your city because lots of windows shattered and maybe some unhappy events happening everywhere. So, but here, completion of this population is only roughly 14% complete. So we need to look even to smaller objects, because even the objects from 0 to 30 meters, there are quite a few of them still out there. We don't know where they are. And so the problem is we need to look for them. The knowledge is the key. So these are the wonderful facilities that are performing the searches. So a few of them are shown here, Catalina Sky Survey and, of course, Pan-STARRS. And so these are the statistics. The two main workhorses, of course, Catalina and Pan-STARRS. They deliver most of the asteroids, but there are many other facilities around the globe. And so this is very nice, but can we do something better at the moment? And so we looked at JPL, we looked at the technology that is currently available. And so we think that it's something that is quite possible today. So this is a farm of four telescopes that we have at Sierra Remote Observatory in California. So essentially, it features 4 telescopes roughly 28 centimeters in size, and it has those wonderful detectors that I mentioned at the beginning. Those detectors are CMOS sensors. Roughly, we reach limited magnitude of roughly 20.8 magnitudes, and so the cost of that system is roughly 5K. So we're talking about telescope, camera, and the sensor. So putting those telescopes anywhere on the backyard of making citizen science, it's very inexpensive. But the productivity rate, potentially, we're talking about 6 news per night. So we reach that productivity right now. If you multiply this by let's say, if you have observing every night, potentially you get into a regime of 2,000 objects per year. So which is roughly the discovery rate of all facilities combined currently. So we're talking about this small bank of telescopes, putting 8 of them together, or maybe distributed around the globe, may be equivalent to something that we already have in terms of larger telescopes. So what the technology which we use here, the key ingredient is technology that we call synthetic tracking. What is synthetic tracking? When we deal with fast-moving and very faint object, we don't see the object in every frame because it's overwhelmed by a significant background noise. If you look here, so if the object is stationary, you have all the photons reflected by this object. They not emit light, they reflect solar light. All those photons are deposited strictly in one point on your pixel, on your sensor. But if the object is moving, it actually spreads photons, and it makes a streak on the detector. And so the streak, the larger the streak, the more less photons you're getting from that object, and less sensitivity you have to detect this object. The key here is essentially to make a video, very fast video on the sensor, and then frame by frame work digitally with each frame. And this technology is quite old. It was proposed many decades ago, but now with new sensors with low noise, high frame rate focal planes that are available from commercial applications like Sony cameras that we have today, and also the high performance computing that is enabled by GPU processing or field programmable gated arrays, we have teraflop computing. Now you can work with frame by frame, shift and add each frame in many velocity vectors. And we deal with many velocity vectors, roughly 10,000 velocity vectors. It's a very significant computation effort. But now with this processors that are available for commercially, you can actually do that. So, but this is not all, because the technology is not really is not fixed. It's actually now new sensors are available, 150 megapixels sensors, which we're now using to actually make a new generation of the same facility that we had, that I showed in the previous chart. So, but to demonstrate the performance of synthetic tracking, so what we have essentially, we used the ZTF data, 1 hour of ZTF data, we were able to discover thousands of asteroids. And thousands of asteroids are some of them main belt, but some of them are near Earth asteroids, meet your new neighbors. So those objects were not known before. It's very recent. It's only two weeks old. We'll report those objects to Minor Planet Center. So now we enter in the regime where we can actually work together not only with ZTF but with other techniques. So what is possible next? Let's look at wonderful facility that is being built now. So essentially, the LSST, which will come online hopefully soon by 2021, 2023. What we expect, it will be primary facility to look for asteroids. But with new technologies, I think with the synthetic tracking telescope, smaller telescope can do very nice job. Essentially, when we look at the 150 megapixel sensor that we have already purchased, and we have a 35 centimeter telescope, now with this type of technology, we essentially putting 100 of those telescopes on the ground. We have performance in detection similar to what LSST will achieve when it will start operating. So essentially, in space, you have a much better sensitivity in space because the sky is darker, and you can actually observe much closer to the sun. And so with this, in 10 years, one small telescope, a 35 centimeter telescope, has a performance of similar to what LSST will achieve. So this is very unique. But now with the low cost of this telescope, you can actually deploy multiple of those telescopes in space. Potentially hazardous asteroids. LSST will saturate the search because it will discover all of the asteroids in one location. But because the orbits are highly elliptical, the sky around Earth changes very slowly. So the key is now you need to distribute those telescopes around the around the sun in heliocentric orbit. And potentially what we're talking about is essentially if you put another facility like LSST anywhere on Earth, the yield of new facility will be only 2%. Compared to what if having just one facility. If you put another telescope in space, 0.5 centimeter, half a meter telescope in space, the gain will be very small. So it's really the saturation that we're dealing without. And so you really need to distribute your systems around in heliocentric orbits around the sun. And so this is what the new technology that I'm talking about is enabling us to do, because you have 35 centimeter telescope, you have the spacecraft buses which costed less than $10 million. And essentially you have the technology to build this and last over 5 years. Now the commercial space industry comes online and enables us to complete the search for all the NEOs larger than 140 meters in only 3.5 years after launch of this constellation. So constellation is really key to go. First of all, you have very high sensitivity of a single telescope. Distributing those 5 telescopes in heliocentric orbit enable you to do a very nice job at roughly $70 to $80 million total mission cost. We have studied that and we're ready to actually move on. So this is our simulations. So this is the typical spacecraft that we are going to be using. It's built by Blue Canyon company in Colorado, small spacecraft, and we can actually do single detection in 5 years. We will complete the search for 140-meter asteroids in only 5 years, discovering 97% of those asteroids. It's looking down to 50-meter objects. It's very interesting because now we can see all of them as well, and so it's valuable input to asteroid mining community. So and this is my last chart. With 5 asteroids, we will see multiple times of those, with 5 satellites, we will see those asteroids multiple times. Seeing them multiple times will allow you to determine orbits precisely. And this is the simulation showing that roughly 90% of NEOs we will see 11 times. That will allow us to determine orbits precisely. And so with orbits, you know where the potential impactors are. And so with the potential impactors, you may either look with infrared follow-up surveys, or you can actually visit those few handful of asteroids that may have the chance to impact in the Earth. Again, the small spacecraft technology. You go there, you determine their masses, property, composition, you know when and what will happen in the next year, in a few years. So that's very unique. And so this is home, let's protect it. And I think the technology that we have discussed today enables us to really make a big leap into detecting and finding those asteroids and protecting the planet. Thank you.
Slava, I think all of us up front here and probably many people in the audience have a very long-standing feeling that infrared is clearly a much better technology than optical for discovering asteroids in space. The question is, where is infrared technology in terms of being integrated into this capability?
In this case, we think that the place for infrared technology is in follow-up mode. Once we determine the orbits, the key, you need to determine first the objects that will cross in Earth orbit very close to Earth. So you know their positions. The next step is to determine the properties of those objects. And so the optical technology will tell you orbit precisely. And then with infrared, you can determine albedos and to determine the masses of those objects and properties.
Well, but the number of photons coming off, small objects get very hot. And so I don't understand why there is the sort of orientation toward optical in terms of discovery and only follow-up with infrared. I'm not interested as much in the characterization as I am the discovery. So I don't quite understand why infrared would not dramatically enhance the discovery rate.
The key here is really the sensor that we're using. So the optical sensor is very much advanced compared to any other technology that we have.
So you're talking the limitation of the infrared technology
that is
the
available
problem.
now, obviously, because to detect and study the fast-moving object, you need to have sensors that will be able to provide very low read noise and to be able to actually to detect the objects and really not to
So is your
produce
problem a trade-off with active cooling versus no cooling required?
It doesn't really improve. So really the technology is need to be improved. The infrared technology needs to be improved to be on par with optical at the moment. And because we're benefiting from the significant investments made in the commercial market now for sensors, it's very cheap. And so when you compare the cost of those missions, when you fly a moderate-sized telescope in space, the cost is it's very high. And as I mentioned, LSST, once it's operational, it will saturate the search. So flying another telescope around Earth will not do the job. Essentially, 90%. Yeah. So essentially, the technology needs to improve, infrared technology.
I think I can add one other thing to it that you did mention, Slava, which is that as you get to smaller and smaller asteroids, they're in general closer to the telescope. Their apparent motions are much higher, and you get trailing losses, infrared or visible. Exactly. The smaller you go, the more it has an advantage because they're faster moving, because they're closer to the telescope. So infrared still has a role, but it peters out just like LSST does at smaller ranges because of trailing losses. So what this does is allows you to get to the smaller ones. It's most effective there, meaning sub 140 meters.
We are not stopping only at 140, we go below.
At 140 meters, LSST does great, infrared does great. At 50 meters, they don't do so well because the apparent motion across the sky is very fast.
We're talking like this, Ed. Yeah. We'll do it later. Okay.
Other questions? So we've got a question in the back.
If an asteroid is discovered, can you forecast or do you know how it moves for the next 10, the next 50 or the next 100 years? Or is it some sort of chaotic theater what's going on in space?
Absolutely. To discover asteroid is not the whole story. You need to know its orbit, so you need to observe it on this, during the few epochs. And so we think that observing those objects within 18 days and maybe another picking up on another epoch, essentially you can propagate the orbit and know orbit very precisely. These detectors I didn't mention, they allow you to do very precise astrometry. So astrometric determination of the orbits will be very, very precise because we use Gaia catalog with 50 microsecond input precision. So with this, you can actually have very precise orbits determined based on the optical technology. Then the next step is really to propagate the orbit. And so you know that the asteroids out there are affected by primarily two forces. One force is gravity, the second force is the sun, the solar solar photons. But in addition to that, there will be maybe some collisions. So to a large extent, you can predict the orbit quite precisely. You need to monitor them. So you know the orbits very, very well, but then monitoring them will be the key. So protecting the planet is not only to discover, you need to keep monitoring because the asteroid belt is evolving. And so evolving by collision, and Jupiter is not playing a friendly role here because it produces a lot of resonances, putting those asteroids in a collision course with us. So that's it's very dynamical effect. But in majority is very well predictable.
The processing unit is mainly for acquisition, or also there is some kind of post-processing, tracking, other information. So the FPGA unit or other processing unit is mainly just to operate the optical sensor and for the acquisition, or you have some extra program for tracking the asteroid or obtaining more information and send if there is specific abnormal behavior or something like that?
It can be done on one processor. So both of those functions still can be done on one processor. But ultimately, I think we'll have a separate processor to determine the orbit and to process the data and then keep the spacecraft functional as well. But now we pretty much baselining using the same sensor, the same processor. On the spacecraft. So the idea is to actually keep the system completely autonomous. We already have autonomous operations tracking from the Sierra Remote Observatory. We can do this on the ground, pretty much determining, looking at the sky and running software autonomously. The same idea is to put it autonomously in space. Essentially, this observatory will just report will send the postage stamps with asteroids.
Question over here from Hayden.
With infrared, do you hope to pick up more of the asteroids' moons?
Could you read? Yes, that'd be helpful. Thank you.
Hayden wants to know, with the infrared technology, do you hope that this will pick up more of the asteroids' moons that you can't observe at present?
With infrared technology?
Yeah.
Infrared technology is very powerful, and so those objects that do not move very fast, definitely infrared can be very beneficial. So the technology that we are discussing, it's really looking at those that are very faint and moving very rapidly, and so majority of those asteroids are around Earth. So, but infrared, it's very good to determine those moons that we don't see. You're right.
Any other questions? Great. All right. Thank you so much, Slava. Next up, assuming this works, which it doesn't. Okay. I think I have Jedicke up, and I'm hoping the slides will start to advance. Dr. Robert Jedicke is here from Hawaii, currently working in Spain. Is that right?
No, I'm going back to Honolulu.
Honolulu, okay. And is with the University of Hawaii. Oops, hold on. That was my... There you go. Let's see if it's working yet. Okay, there you go.
All right. So I'd like to describe my path to Hawaii. When I was an undergraduate at the University of Western Ontario in Canada, I studied physics, and then after I graduated with an undergraduate degree, I actually tried to play professional Canadian football. That's not American football, it's different, and it's not European football. But of course, if you're a European, you would look at Canadian football and think it looks just like American football. I then got a PhD in particle physics, and I was a particle physicist for a little while, and then I became a software engineer. And finally, after many years, 16 years ago, I went to Hawaii to work on this project here, the Pan-STARRS project, and help them build this telescope on the summit of Haleakala on Maui. And I find it really interesting because when I was a teenager, if you asked me what I want to do with my life, I would have said I want to be an astronomer in Hawaii. The reason for that being that when I was a teenager, they were building at that time what was the largest and best telescope in the world, the Canada-France-Hawaii telescope on the summit of Mauna Kea. And I was inspired as a Canadian, realizing that Canada had half of this telescope on Mauna Kea, and I thought this is the place for me to be. That's the place I want to work. So I took a circuitous route, but I eventually got to Hawaii, and I'm an astronomer there. So it's really wonderful. This Pan-STARRS telescope is kind of like old technology relative to what we've heard about already from Lynn and from Slava. This is built 15 years ago now, so it it's sort of based on technology and ideas that were sort of developed 20 years ago. But it's been a very productive telescope for finding the hazardous asteroids. In 7 of the last 8 years, Pan-STARRS has been the most prominent project at discovering the potentially hazardous asteroids. The potentially hazardous asteroids are the ones that may hit the Earth someday. We don't care about asteroids in terms of their hazard between if they have orbits between Mars and Jupiter. We don't care about even near-Earth objects. Near-Earth objects only come near, it's actually a bad term. Near-Earth doesn't mean they can actually come near Earth at all. Potentially hazardous objects may come close to the Earth. A potentially hazardous object is any object that's on an orbit whose orbit comes within 8 million kilometers of the Earth's orbit. So 8 million kilometers sounds like a large distance, but it's actually relatively close in the solar system. And since these objects can come close to the Earth's orbit, they are the ones that are the most hazardous for us. And Pan-STARRS is the best telescope in the world for finding these hazardous asteroids. Now, the reason that Pan-STARRS is so good at finding these things is because it's at the summit of a 3,000-meter high mountain in Hawaii. Now, I think a lot of people don't realize that we have these very high mountains in Hawaii. The tallest one is Mauna Kea, which is 4,000 meters high in Hawaii. It's very cold up there. I've been up there in May when it snowed. It gets very cold, and I've been evacuated from the mountain because of a snowstorm. So we have major snowstorms in Hawaii.
Well, that's the one on the right.
Yeah, Mauna Kea is right there. Yeah. And so this is Mauna Kea, the 4,000-meter high mountain seen from the summit of the 3,000-meter mountain, Haleakala. Now, so we're very high. We're also very remote, because Hawaii is in the middle of the Pacific Ocean, thousands of kilometers from any other large bodies of land. And the nearest city is Honolulu, which is still a few hundred kilometers away. So it's very remote, and it's so high that actually the clouds, as you can see here, are below the summit. So that the clouds actually block the light from any other small cities that are around from the summit. It also has very dry air, which is very good if you want to do infrared observations. And it also has very stable air. The air that flows over the Pacific Ocean has a long time to sort of steady out. And then the mountains, the volcanoes in Hawaii have very shallow slopes. You can see right here the shallow slope of Mauna Kea. It's not a very steep slope at all. It's very shallow. So when the wind blows up the top or blows over the surface of the volcano, it's very, very steady and very nice flow. We call it laminar flow over the mountaintop, which provides some of the best conditions for astronomical observations in the world. The other thing that makes Pan-STARRS the best telescope in the world for finding these potentially hazardous asteroids is its camera. In 2008, just 10 years ago, Gizmo Watch proclaimed the Pan-STARRS camera as one of the top 20 engineering marvels of the world. And at that time, it really was. This telescope has got 1.5 billion pixel camera. Now remember, you probably have a nice digital camera. That digital camera probably has something like 15 million pixels on it, right? So this camera here has 100 times as many pixels on it. And while the little sensor in your camera is called a CCD, is maybe the size of your fingernail, your small fingernail, this camera here that we see, this is the active area down here, all this sort of shiny stuff that you see. These are all the CCDs. This is about the size of a standard chessboard, right? So compare your little fingernail to the size of a chessboard. That's 15 million pixels, 1.5 billion pixels. And we've actually created a map of the 3/4 of the sky, all the sky that you can see from Hawaii. And from Hawaii, you can't see the sky over the South Pole. But for the 3/4 of the sky we can see from Hawaii, we've created a map of the entire sky that contains, let's see, it's 2 billion megabytes of information. Right? So it's a map of the entire sky where if you were to sort of compress it down to the size of the Earth, it would be a map that has a pixel size of 6 meters. So within this room right here, there'd be something like 10 different pixels on the map of the sky. This telescope allows us to detect asteroids that are 1 million times fainter than you can see with your naked eye on the darkest possible night. So if you imagine the darkest place you've ever been in your life, looked at the sky and just been amazed at how many stars you could see, we can see stars and asteroids 1 million times fainter with this telescope system here. And finally, this system is great because it has a field of view that's very large. It's the size of a chessboard, but if you were to take an image of the sky, you would be able to fit about 35 moons onto this image. Right? So it's about 6 moons across. You could fit 35 moons onto that entire area. So this has got a tremendous field of view, and it can see objects that are very faint. So all those things combined allow us to detect very interesting objects in the solar system. Like this object here, Oumuamua. Oumuamua is one of the most interesting, fascinating objects that Pan-STARRS has found. It is the first and so far only interstellar object. This is an asteroid or comet, depending on who you're talking to, that was found passing through our solar system. All the other things that people are talking about, these near Earth asteroids, potentially hazardous asteroids, they're all within our own solar system. They're bound gravitationally to our sun. But Oumuamua is not bound to our sun. It came into our solar system, and when it passed by the sun, it was moving at almost 90 kilometers per second when it passed by the sun. And it passed by the sun at 1/4 of the distance that the Earth is from the sun. So at 90 kilometers per second, you can get from Luxembourg to Paris in just over 3 seconds. Right? So that's extremely fast. And that's moving so fast that the sun's gravity cannot stop it from leaving our solar system. It came into our solar system and is going to leave our solar system, and it's never ever going to come back. We're never going to have another opportunity to see this object. And in fact, we hope to see these kind of objects. We built Pan-STARRS hoping that we would see these kind of objects. We didn't think we'd see it. So the fact that we saw it implies that there's more of them out there than we thought. And the LSST that Lynn talked about, they hope to see, based on the current predictions, they hope to see about 1 per year now. So as opposed to finding the first one ever, we're now going to hopefully get 1 per year with the LSST project. Now, Pan-STARRS has found a bunch of other interesting objects as well. Just 7 days ago, it was instrumental in obtaining observations of an asteroid that actually hit the Earth just about 300 or 400 kilometers south of Puerto Rico. There was an asteroid, a very small asteroid, about 4 meters in diameter, about the size of a car, that struck the Earth 400 kilometers south of Puerto Rico, and Pan-STARRS actually got observations of it. The very first observations of it were taken by another telescope system in Hawaii called ATLAS that Lynn mentioned very briefly. But in the future, and finally, so this is the path trajectory of Oumuamua coming into our solar system. Oumuamua means, by the way, in Hawaiian it means a messenger or a scout from the distant past coming to visit us, right? So it's a very nice Hawaiian word. So most comets in our solar system have these very elliptical orbits. This Oumuamua came sort of straight into our solar system, passed very, very close to the sun. The sun's gravity, this is a blow up of the area where it came in close to the sun. It came in very close to the sun, and the sun's gravity bent its path, and then it sent it out the solar system, and it's now going off in an entirely different direction. But in the future, I hope to get involved, or I am starting to get involved in asteroid mining, and I hope that projects like LSST and space-based projects as well are able to find asteroids that can be mineable. I'm working with a project, a company called TransAster Corporation based in Pasadena, California, and they have this idea. They want to bag an asteroid and then use the fact that solar energy is free and extremely powerful in space. They want to have giant inflatable mirrors and collect the light, send it down in a concentrated fashion onto the surface of the asteroid, and literally burn the water out of an asteroid. The water vapor fills the bag, and then it finds its way into what we call a cold trap. These are bags of basically empty bags that are exposed to dark space. You're not allowed to see any sunlight at all, so they're very, very cold. So anytime water vapor from the bag enters into one of these cold traps, it freezes into solid ice. And then all you have to do is disconnect the ice bag and bring it back to wherever you want and sell it to your customers and make a lot of money. Thank you very much.
Great. Now, questions from the panel first?
Rob, in the old days, you were going to have a lot of Pan-STARRS. I remember up through 4. We're up to 2.
Thank you for bringing back that painful memory, Rusty. Yes, we were supposed to have 4. When I joined the project 16 years ago, that was my goal, was to build 4 telescopes. And in fact, you can almost think of Pan-STARRS as a mini LSST. It was sort of a precursor to LSST. And we only built the one 10 years ago, and it was operating very well. Just recently, we got the second telescope up and running, and there is no plans to build any more at this time.
And that's not because of us, but because of the Air Force.
Well, I don't want to point any fingers at anybody. I'd say that the astronomers are somewhat culpable.
Great. Well, then, to the audience, any questions for
I don't want to take away everyone's time, but Oumuamua, I never can pronounce that, very much reminded me of a book from Arthur C. Clarke, which is called Rendezvous with Rama. And I hope you have researched whether the orbital data from Arthur C. Clarke match your object.
I have not, although I've heard that other people have done that. It sparked a lot of interesting debate. That one object has got, I forget how many papers have been already written about it, something like 100 or so. And most of them make a lot of sense. There are some people who claim that Oumuamua may be an interstellar spacecraft that was sent in from another civilization, maybe not on purpose, maybe it just sort of happened to fly through our solar system. I think that there is absolutely no evidence that supports that idea, even though it can be some very prominent scientists who are claiming that it's reasonable. There's all the evidence supports that Oumuamua is a perfectly natural object that has, in fact, its trajectory through our solar system matches exactly what was predicted in a paper that I wrote 6 months before Oumuamua was found. And its rotation rate is identical to the rotation rate expected for objects of that size. The craziest thing about it is its shape. right? Its shape is unusual, but even then it's unusual only when we compare its shape to objects of the same, of much larger sizes in our own solar system. We don't have a lot of objects of that size that we can compare it to in our solar system, so we don't, I'm uncomfortable saying it's a very unusual shape at this point in time.
Great. Any other questions up here?
I have a question about its trajectory, since you had calculated that, I guess. But so it seems to me if you observed something passing through the solar system, it would be more likely to miss the sun by a larger distance. Is that an observational bias, or, and if so, you would expect a lot more of these, right, unobserved objects to be coming through the solar system? Or is there some gravitational focusing reason for that?
Right, so the question is, why did this particular object, this very first object that we're finding coming through our solar system, pass so close to the sun? And as you said, it's an observational selection effect, right? So in the paper that I wrote, that, yeah, as I said, was published 6 months before it was found, we considered two types of objects, comets and asteroids. And comets can be seen when they're much further away, because they create these coma, they eject a lot of gas and dust, and the gas and dust makes them visible from much larger distances. And so the kind of comets that you could find on interstellar comets you would find are quite different than the kind of interstellar asteroids you would find. And so the paper that we wrote was the first to consider actually interstellar asteroids. And if you consider an interstellar asteroid something that doesn't create a lot of gas and dust, then in order for them to become bright enough to be seen, they have to pass in close to the sun. And then when they pass close to the sun, then their orbits get bent exactly like this one did, right? So it basically matches exactly what we thought this kind of asteroid should do. We just didn't think there were that many out there. In fact, we used our paper to estimate but based on the fact that we had not yet seen any, we used that to show, to estimate how many there could be, or what's the upper limit to how many could be. And so because one was just found months after our paper, it meant that the actual value was very, very close to what we said, which is exactly what turned out to be.
So the second part of that, then, the implication is, because of that selection bias, observational selection bias, because Earth is close to the sun, that means these objects like this must be flying through the solar system all the time, right? We just don't see them.
Right. So now you can now that we have Oumuamua, we can estimate that, and assuming that Oumuamua is average, right? I mean, we could just be lucky, right? We could have just been lucky that this one interstellar object came through, right? You know, maybe, right? But let's assume that we're not lucky, that it's just an average thing and it's a representative of a larger population. Then at any time, right now, there are 3 interstellar objects of Oumuamua size or larger within the Earth's, closer to the sun than the Earth is. Right? It's just that they're very hard to find. Right?
Rob, I heard you say something that directly conflicts with everything I've read. That is, it seems to me that all of the aberrant ideas about this being an alien spaceship have been based upon the fact that this does not behave gravitationally, that its trajectory in fact deviates from a gravitational trajectory, and all sorts of speculation about this being about as thin as a piece of cellophane, that kind of thing, a light sail sort of thing. I heard you say that it matches your gravitational projections of the trajectory exactly. So is this a fundamental disagreement in terms of measurement, or what? How do those two things work together?
Well, I think that me and many other scientists that do this work would claim that it's a misinterpretation of data from, by the people who are claiming it's an interstellar spacecraft, right? That you're right that the object that's coming in, it does not follow exactly the trajectory you would expect if it was an inactive asteroid. If it was an inactive asteroid, it would fall into the solar system and then go out in a way that we could predict exactly. But if it had, for instance, a little bit of water inside of it, and that little bit of water was heated up as it passed close to the sun, and now it's creating this jet of water that's coming out, just like a comet, right? But a very,
so why are you not seeing the outgassing then, is the question with that?
Because we're seeing a change, we're seeing that the trajectory that it's taking is not exactly like an asteroid, it's more like a very, very weakly active comet. But it's so weakly active that that you cannot detect it with modern with ground-based telescopes. You can't even detect it with Hubble. Hubble Space Telescope took an image of this object, and it looks like a perfect star-like object. There's just nothing about it because the deviation from the trajectory we would expect if it was inactive is extremely small, and it's perfectly consistent with there being just a little bit of activity generating this force. And also, in terms of it being a very thin light sail that's very large, we know from Spitzer Space Telescope, which looks in the infrared, we know how big this object is, right? And so we know a lot about things about this object that are just being ignored by some people.
For what reason? No.
Thank you, Dr. Jadaki. And next up is Dr. Patrick Michel, who just flew back in from Tucson. Is that correct? And is the primary investigator on two really exciting asteroid missions that are out in space right now, OSIRIS-REx and Hayabusa 2. And we have 15 minutes for your presentation, and then we'll do Q&A, and we'll go to the reception afterwards. So thank you.
Okay. Thank you. Anyway, don't believe Robert. He's from Oumuamua. That's why I try to justify it's not a space. Okay, so let's see. Yes. Oops, sorry. So we looked at the ground, and now we're going to go to space. So I'm also a space explorer, but contrary to my colleagues here, I don't have the courage to go in a rocket, so I do it from the Earth. And thanks to Robot, you can still do something. So as you know, Asteroid Day is now, it's the 30th of June because of Tunguska. But today is also an anniversary which is very important. It's the anniversary of the first image of a carbonaceous type Near Earth Asteroid. In 2018, 27th of June, Hayabusa 2 reached Ryugu, which is a 900-meter asteroid, and you see this image. So there is a time in history where before this image, we didn't know anything about what we call C-type object. We don't have any detailed image. And after 27th of June, we got this image. And we have now the luck to have two asteroid missions that are currently visiting their asteroids right now. One at 120 million kilometers from Earth, which is OSIRIS-REx from NASA, and the other one, Hayabusa 2, which is about 340 million kilometers from Earth, so about 1,000 times the distance of the Earth to the Moon. So I'm going to talk to you about what happened during this last year, because this is absolutely spectacular, and it also shows that space is hard. You don't do what you want to do. It's tricky. Asteroids are a challenge, and you're going to see why. So we have these two asteroid missions, which are actually sample return missions. So we want to go there and come back, which is the trickiest path. So we have OSIRIS-REx, which was launched in September 2016, and Hayabusa 2, which was launched in 2014. So this is a Hayabusa 2. It's actually a small spacecraft after Hayabusa, which was the first sample return mission by JAXA. It's hovering, so it's not orbiting the asteroid. It stays at 20-kilometer distance from the asteroid. Then it has target markers to be able to navigate and do close proximity operation. And the aim is to collect some samples, which what we call a touch-and-go approach. So basically, you have a horn. When the horn touches the surface, there is a projectile which is fired at 300 meters per second, and you collect the ejecta from the projectile in the horn, and you go away. Because from an asteroid, it's very complicated. You have low gravity. Everything can move. You don't want to stay on the surface too long. It's also very hot. So let's see, this is 27th of June last year. This is what we got. And I can tell you that I'm sure my astronaut colleagues, the first time they saw Earth from space was totally crazy. But for us, we are still on Earth. When we receive the first image of such a body from 340 million kilometers away, it's absolutely crazy too. Especially because it doesn't look like at all what we predicted. This is the shape that was estimated by light curve, a sort of spheres. And actually, we have what you call a top shape. It's a spheroid with an equatorial bulge, which is typical of primaries of double asteroid. And it's not a double asteroid. The other thing which was surprising is the amount of rocks that we have on the surface, despite the low gravity. And what you don't see here is that it's very dark. It's blacker than anything you have on Earth. I had a model, I forgot it, but even what you have on the road is brighter than this asteroid. It's totally dark. So, of course, here we increase the contrast so that you can see something. But it's even darker than the screen here. It's also very light, 1.1, 1.2 grams per cubic centimeter, so just a little heavier than water. If you put it in the water, it almost floats. So it's really crazy. So this was the first image, and of course I went to see Brian May with some of my colleagues here. We went to Milano, Mark and Yvonne, etc. And Brian is also an expert in stereo images, and he did stereo images. I actually have the glasses with me and a lot of images, even non-public ones if you want. It's totally crazy, and also you learn a lot scientifically. It's fun because you are on a new world in 3D, but also you learn a lot scientifically. So that's really great, and of course you know who it is. And these are the first images. I'll go fast, but we deployed 2 mini rovers in September 2018. This is also a first in history, the first successful deployment of mini rovers on an asteroid surface. And you can see here the sun rising and the sunset. So you are on your transat, you know, like on the beach. And of course, it's not 24 hours, 12 hours. The rotation rate is 7 hours only. And it looks like the floor of oceans, basically. And again, when you receive this image, it's really a big emotion. You see it's a lot of gravers. We don't have any finds. So this is something that surprises us. It's pebbles and rocks, but not many finds. And we still are trying to understand that. Because what you need to understand is that all our assumptions were wrong, as usual. And we are still there, and so we are still trying to understand what we are seeing, despite the fact that you have also to do the complex operations. So then we deployed the French-German lander. You can see the little box here. That was on the night on the 2nd to 3rd October. I could tell you the story of what happened, because everything never works perfectly, but eventually it landed, and it could take marvelous data, including images, and also measure the porosity of rocks, etc. So a lot of things were done with this, again, first deployment of a lander of 10 kilograms. And then we did the sampling. So the initial strategy of sampling had an accuracy of 100 meters on the surface. So basically the spacecraft go down, and you don't know within 100 meters where it will touch down. It was too much, because we didn't have any place larger than 6 meters, which was safe. So the Japanese has to revise entirely the strategy. I could tell you more about that, in order to go from 100 meters to 6 meters. So they made some rehearsals. We replayed the first sampling that should have occurred in October 2018 with some rehearsals. And eventually it was decided on February 22nd to do the touchdown. And I had the great honor and sense to be in the operation room at that time. So you see how it works. You have a small projectile, 300 meters per second, and then you collect the ejecta. So this is basically the sampling zone, 6 meters. We deployed a target marker to guide the spacecraft, but as usual, nothing happens perfectly. And unfortunately, it bounced and went off where it should be. But despite of that, we decided to go and try to guide ourselves in a direction which is not supposed to be the one where we want to go. So it's a little crazy. And you can see that at the end, I can tell you already the solution. We hit it here, just close to the center of the circle. So wow, strike. So this is an image. So basically, in the operation room, we had a lot of things that I could tell you about, and we had to wait about 5 hours to get the first images. So we knew something happened, we didn't know what. And I can tell you that at that time, the 5 hours after 24 hours without sleeping were totally, it was terrible. So the operation room in Sagamihara, close to Tokyo, and there is nothing. And I remember myself walking and looking at my watch and doing all the supermarkets, saying hello to everybody. It's crazy. And then eventually I come back to the operation room, we talk, and we hear somebody screaming, "Eto!" You know, the Japanese. And then we got this image. So we have the sample on. It's a small camera by donation, by the way, which is connected to the spacecraft. And then you see the descent. So it's going very slowly, 10 centimeters per second, because there is no gravity. And in 1 second, it will fire the projectile and go up with the thrusters. So for the moment, nothing happened. You see the shadow of Hayabusa 2, by the way. This is the surface of Ryugu. And then, you're going to see, it touched the surface. It was 1 second. Up. Boom. And then, look at the amount of dust. So that was the first time we were able to do such a thing. We have a lot of dust around, meaning that a lot of dust came into the horn. We target to have 100 milligrams. I bet we have more. You can see here the comparison between not the comparison. After the touchdown, you can see all the dust around, and even and that's I had another image to show you. And this was the celebration in the operation room, of course, after that. We knew we succeeded that. But because it's not enough complicated, we did something else. In April 2019, so 5th of April, we deployed this little box, which actually contains an explosive, of course. And the spacecraft went behind the asteroid to hide, because when you have an explosive, you don't want it to explode with the spacecraft around. When the spacecraft is behind the asteroid, you make the explosion, you give a kinetic energy to a projectile of 2 kilograms that will shoot on the asteroid at 2 kilometers per second. So this was the first hypervelocity impact experiment at asteroid scale. You can see that. So it's quite dangerous. And we are very scared because we already had the samples. You know, you don't want to screw up, sorry to say it that way, but after having the sample already, and you can come back. But I was part of the experiment. I really want it to be done. And this is the operation room. You can see myself here. So basically here, we deploy the projectile. Then we go on the side. We deploy a small camera to observe the impact. And then we put the spacecraft behind the asteroid to protect itself. And we got effectively, 2 weeks later, we got the crater measured. So there was an impact. We have a crater which is much bigger than the calculation we did, which predicted 2-3 meters, is more than 10 meters in size, which showed that the extrapolation of our knowledge from laboratory experiments to asteroid scale still has a few issues that we need to sort out, which is very interesting. The thing that I need to say is that, so that was the celebration. After that, the target was to do a second touchdown in order to grab some samples from the subsurface close to the crater. I was in favor of not going because we succeeded everything. We could go back peacefully. We have samples. 2020 would be the first to come back with samples. And the Japanese decided to go. And they will on the 11th of July. I don't know if it's public yet. I think so. I asked Makoto. I think he told me I could say it. 11th of July, there will be a second touchdown. Yeah. Okay, so now OSIRIS-REx, to go fast. So OSIRIS-REx is a NASA mission, New Frontier. It's a very big mission. So here, it's a safe approach. We don't have landers, rovers, impactors. We concentrate on the sampling. And here we target 60 grams to 2 kilograms. So it's a much more massive sample that we'll get, and everything is done to make sure we get the sample and go back to Earth. This is Bennu. So it's a 500-meter asteroid. Ryugu was 900 meters. You can see these spectacular images. The cameras are fantastic. It's like you were there. And again, the same shapes as Ryugu. So there is something really, it's not a coincidence. We don't think it's a coincidence. They have the same shape, same albedo as dark, same density, 1.2. I mean, maybe we went to the same one, we don't tell you. But we could think so. And a lot of boulders. But there are actually many differences too, which maybe for the average man not necessarily important. For us, very important. One of them is the hydration band. So don't worry about the curve, but basically it contains hydrated minerals. So it's so water. It has phyllosilicate, deep band, so there is a lot of water. On Ryugu, there is some water, but it was dehydrated, we believe. So there is water there, which is very interesting for resources, and also the fact that what we want to determine is whether asteroids contributed to the emergence of life on Earth. We know that there were a lot of impact at the end of Earth formation. They could have brought the water. We know that the water-ocean properties are the same as the water on asteroids already. But for the organic material, we want also to verify whether the structure of this material is the same as the one that makes the living people. And with the sample, we'll be able to do that. So it has water. Look at these images, just to show you a few images. It's fantastic. So here we are orbiting. So we are not hovering. And this is the closest orbit ever made around the body in space by OSIRIS-REx. And basically, it's like you are on a helicopter and you go wherever you want. The flight dynamics people are fantastic. They go wherever we want. You can see here this kind of images, totally crazy. For the geologists, it's a dream. They can explore many things. There are a lot of different rocks. We don't understand yet what it is. The more we know about asteroids, the less we understand. That's always the same. And here you see the amount of boulders. And another one, Ben, which is very big, very dark. There are a lot of fractures. I mean, you could spend hours on these images. And remember, we are not on Earth, because I see that in my field. But I have wind, I have humidity, I have erosion. I can explain. Here, I have nothing, except micrometeorite impact and maybe thermal cracking due to the thermal cycles. So complicated to understand that. And the big surprise was we saw ejection of particles. It's an active asteroid, and that replies to Rusty's question, because this you cannot see it from the ground. So it's active, and we could only see it when we were there. And it must have a teeny effect on the trajectory. So maybe Oumuamua, maybe you don't come from Oumuamua finally, Robert. Maybe there is a solution. Just a quick thing, very interesting, I mean, very funny. We discovered that on the 6th of January. We are starting to write the first paper for Nature. And then somebody comes in the room in Tucson and say, hey, we got particles. And so we look at that and we start to measure the velocities under constraint. We are a little worried. And in principle, in that case, you have to call NASA headquarters and to ask them whether there is we need to go to safe mode 100 kilometers away because there is a danger, which would, of course, postpone all the operations, etc. So we hoped they would say we still stay there, but we know they are conservative. They may say no. And we were saved by Donald Trump. Because, for once, there was a shutdown of the government at that time because of the mess. And because of that, when we called NASA, you know that the public servants are forbidden to answer the phone, their professional phones, when there is a shutdown. So we couldn't have the approval or the refusal of NASA to continue, so we just continued, and we saved the mission. So thank you, Donald. So we have an active asteroid, so we demonstrate we don't know yet whether the activity due to water or micrometeorite impact is not probable, but maybe. Bill Bodke thinks it could be probable. So it's very interesting. We are really continuing to explore like Christophe Colomb, like the explorer when they went to space. We have now the luck to be able to do it from the ground. And really we discover 2 new worlds, and we have many debates because there are still things we really need to understand, which is very fantastic. I'm going to talk to you about what next, in particular for Europe. And I am 10 seconds late, but in France, we are always late, so that's okay. So it's 2 minutes. So it's DART and ERA. It's called the IDA project because this is related to Asteroid Day original objective, which is mitigation and protection of Earth. So this is the first asteroid deflection test using a kinetic impactor. So basically, we shoot a projectile at 6 kilometers per second on the moon of an asteroid so that we modify the trajectory of the moon around the primary and we don't make a mess with the primary itself. And then we observe the outcome with a European satellite because DART, which is a projectile, will be made by NASA and is secured for launch by SpaceX in July 2021 from California, the first one from California. And then ERA, hopefully, if it's approved by ESA at the Ministerial Council of November, will come later to go to the crime scene and measure the crater size, the internal structure of the body with the Luxembourg CubeSat, and measure the deflection. This is just to show you the Ryugu, and the size of the target is 160 meters. It's really small. This is the size of Didymos. We call it Didymos because the binary is called Didymos, so we call it Didymoon. It's only 160 meters. So that will be absolutely fantastic to see what a space rock at this size look like in space. I mean, something we don't really know, basically. So that's going to be interesting. A lot of science will come out of it in addition to the deflection. So I stay here just to show you the perspective in small body missions. We have OSIRIS-REx Hayabusa 2. We have maybe DART and HERA. MMX, which is a Phobos sample return mission, so Martian moon, a very small moon. Very interesting. We have Psyche at Psyche. Psyche is a metallic object by NASA. We have Lucy, which will make flybys of a Trojan asteroid, the one that shares the same orbit as Jupiter. Maybe Caesar, which is a sample return from the comet 67P that Rosetta visited. It's not sure it will go. It is competition. And as you can see here, it's all NASA, JAXA, NASA, JAXA. ESA made Rosetta, and that's why we need ERA, because we need to keep the expertise and to contribute to this golden age of asteroids, because as you see, it's absolutely fantastic, and it can fire the imagination of the young generations, which is also an important purpose. Now I'm super late, and I'm going to be killed. Thank you very much.
Hello, Patrick. I'm very glad that all of you had such interesting presentations because here are not only scientists, it's a general public also, and I want to greet also the ambassador of Romania who is present here. A few things about how the scientists choose a specific target to send the spacecraft to, because there are there is a so high diversity of asteroids with so different compositions. And of course, we want to know as much as possible about many types of them. But how do you choose a specific target? Thank you.
Thank you for this question. Actually, yes, it's a very important question. And so basically, first of all, we define our science goals. So if we take Hayabusa 2 OSIRIS-REx, for instance, the science goal was to collect a sample from a carbonaceous asteroid. When I say carbonaceous, it's interesting because we are not sure yet they are carbonaceous. We have just spectral observation from the ground, and we don't really know the composition. We know they are dark. There are some spectral features like maybe hydration band, the fact that there is water, but not much more. Interestingly, the comet that Rosetta visited for 2 years, we still don't know what it is made of, although we were there, because they have very low signatures, so we need samples. But we make an assumption that the dark types are carbonaceous. Then we take the list of all the carbonaceous objects, and then there are other criterion. If you want to take a sample, it should not rotate too fast, so you eliminate all the objects which have a rotation rate lower than 3 hours, basically. And then the driving thing then is the cost. You need to define the mission scenario that allows you to remain the cost cap, because these missions are always in competition. So, for instance, OSIRIS-REx was in a New Frontier program, which is $800 million without the launcher. And so you need to remain below the 800 million. So operations, the time, so how much time it will take, because the operation every year accumulate. So everything then come into play to put the cost as small as possible and remain the cap. So, so for instance, Psyche, they wanted to go to see a metallic object. So they took a spectral type which looks like a metal, although there is ambiguity. We are not sure anymore it's a metallic object. And then you look for the target that allows you to do the mission again in the cost cap, this time of the Discovery program, which is $450 million. So it's always a question of cost. If you have infinite cost, then you can do more things. But as I said, the size and rotation rate also come into play once you have your spectral type defined. And in fact, interestingly, when Hayabusa 2 and OSIRIS-REx were under study, despite the fact that there are a lot of C-type asteroids in the Near Earth object population, only 2 were reachable, Ryugu and Bennu. So one had to go to Bennu and the other one to Ryugu, because it's a question of delta V from the Earth. So that's what's interesting. Yes? I hope I answered your question.
When does a decision need to be made on Hera in order to still get there before dark hits it?
So in that case, you have to be able to use a general relativity and go in the past, because unfortunately, the decision had to be made at the last ministerial council of ESA in December 2016, where we failed to get the funding, and in that case, we would have been at the same time as DART. Now we hope that it will be approved, in any case the last time, and we will arrive 4 years later, but that's okay. Why? Because, of course, we lose the spectacle and the message to the world. We do international cooperation all on the same time together. That would have been fantastic. But in terms of the goals, we are okay, because for the first images of the impact, we'll have a small CubeSat, Italian CubeSat that will be deployed called Licia, which will take the first 300 seconds of the impact. So we'll have at least the ejecta part. And then coming 4 years later, fortunately, on astronomical timescale is nothing. So the crater won't have changed, the mass of the moon won't have changed, and all the measurements you want to do to assess the deflection efficiency can be done 4 years later. I agree with you, I would have preferred to be there on the same time, but the main objective can be kept even afterwards. Of course, if the decision is not taken this year, we know, I mean, yeah, it's finished.
Just one step further, where specifically is the funding for Hera? Are you
Okay.
in phase A?
No. So we are now entering phase B2. And the phase B2 will stop or continue depending on the decision at the ESA Council. So if you want just a little more explanation, at ESA you have several programs. One is mandatory, it's a science program, so the money is there. Then after, it's just a competition being selected or not. We also failed to have Marco Polo, which was another sample return mission. We failed a lot of time, actually. This one is not in the science program. It's in an optional program called Space Safety, which is a new program proposed by the director Werner of ESA, which includes space weather, deorbiting space debris, and planetary defense. And EHA will be proposing this program because that was a problem before. There was no program for neither Don Quixote nor ERA. And therefore, when people want to pay, they want to know where they pay. Technology program, they don't like that. So we put in place, for once, a space safety program. And now, since it's optional, not all ESA member states they have to pay. Everybody can decide to pay and how much. So these 2 days of ministerial, there is Ariane 6, ISS, everything. And it's like, a tapestry market where everybody goes and many things in the corridor with blackmails. You don't pay for ISS, I don't pay for air. I mean, I shouldn't say all that. It's how it works. It's a little dirty. Who should we talk to? Yeah, you should talk to the delegates of the member states. You have one in Luxembourg, but I think he's motivated, but never enough. So you see, to the delegates of the member state, these are the ones that decide to do it or not, and it's a competition. But last time we did a fantastic job. We had Greg Richter help us to have a letter signed by Nobel Prize, blah, 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 etc. At the end, it doesn't count as much as I thought. I shouldn't say all this, but the thing which is, that's why in Europe it's complicated, more than with NADA, is because you have 25 countries. It's actually Jean-Jacques Dordain who told me that once, the former director. No, but it's true. You have 25 countries, and basically you have one election every year somewhere. So you never have the same people to talk with. And the policy of every state changes all the time. So for an optional program, you may have, a prime minister motivated, and then he's fired, and the other one comes, and he's not motivated, and that's over. So it's super complicated, in fact.
Just a remark on lobbying. 8th of October, Europe-wide series of space talks will take place. ESA initiated space talks, and that is the point to sum up your support for certain missions, because this is exactly what ESA wants to bring to the ministerial, the opinion of academics and the educated public, what missions to promote and where to spend the money. So 8th of October, and hopefully also in Luxembourg there's some support to that.
Yeah, please talk about ERA, because seriously, this is the only opportunity of an asteroid mission in Europe for decades, because there is no other plan at all. There's nothing. It's just there is now Comet Interceptor that has been selected for 2028. It's a small mission. It's for a comet which is not known yet. But, I mean, the expertise of Rosetta and the young generation that had been hired in this field, they want to have a mission, and this one is going to be great. But, I mean, of course, I'm not biased at all.
Thank you, Patrick. So in closing, we created Asteroid Day really to raise awareness about asteroids, asteroid science, asteroid missions like Hera, like OSIRIS-REx, and like the work that's happening here in Luxembourg relative to space resources. And so the conversation will continue in our reception just next door. All of our panelists and all of our speakers will be over there to talk to you. I'm taking a couple of them to a global press conference upstairs in about 20 minutes. And I invite you to continue the conversation out in the lobby. And I want to thank again all of our sponsors. We wouldn't be here today without the really generous support of the community of Luxembourg for us to be able to have these kinds of conversations where we bring these truly remarkable people here to your country to talk about something that they're incredibly passionate about, asteroids and planetary defense. So let's continue the conversation in the reception and thank all of our speakers and panelists.
Rusty, we didn't say hello.
This should be the output of this.